Hello everyone, this is my presentation for Milestone4 for the AetherMart project. So during this presentation today we'll be going over the MariaDB cluster troubleshooting and performance analysis. Then we'll move over to advanced ETL data pipeline design and implementation, as well as MariaDB vector embedding generation and similarity search, and then refined AI data preparation, and finish AI disclosure and end. So let's start with MariaDB troubleshooting and performance analysis. So first we're going to start with query performance. Here we're doing this explain statement, which shows how the database executes a query on the customer table when filtering by customer ID. We can see that MariaDB uses the primary key, which means that the query is optimized. It only scans one row instead of the entire table. The access type is const, which is the most efficient possible for a lookup by unique key. This confirms that our index. Okay, that's the what we run, and then we did the same thing for products, searching by product ID. And orders with order ID, we got the same results, so very similar. And then we did show status like WS rep percentage, and this is what we see. So here we can see the result of the command, which displays Galera's internal synchronization and replication metrics. The key indicators confirm that our cluster is stable, synchronized, and fully operational. We see that WS rep ready is on, the node is ready to process queries. WS rep connected is on, the node is successfully connected to the cluster. WS rep local state commented is synced. This means that all nodes have the same dataset and that no replication lag or desynchronization. The cluster size is 3, that confirms that all 3 EC2 nodes are active and part of the cluster. And WS rep cluster status is primary. The cluster has quorum and can continue serving requests even if one node fails. And flow control paused is 0, which indicates that there is no replication throttling. The nodes are applying transactions smoothly. Then we did show engine InnoDB status G. So here we have some screenshots, and here we have a summary table. Here we can see that this output comes from the command shown before, which provides a detailed internal snapshot of the InnoDB storage engine. From this report, we can confirm that the database engine is healthy and performing efficiently. The history length is 0, meaning there are no unpurged transactions and no backlog. InnoDB is keeping up with the transaction cleanup. There are no pending reads or writes, so all input-output operations are up to date and the cluster nodes are synchronized. The buffer pool is around 8,000 pages, with only 1.67% of dirty pages, which indicates excellent memory management and no excessive write load. The log sequence numbers show consistent progress with no pending fsyncs, confirming the redo log is being flushed properly. The transaction sections show all sections are idle, means there are no deadlocks, waits, or log connection were detected. So overall, this demonstrates that our MariaDB Galera cluster is not only synchronized, but also running with optimal storage performance and no bottlenecks at the engine level. And then we want to check this low query analysis, so we did sudo nano etc mysql mariadb.conf 50 server cnf, and then here we saw like the key buffer size, max allowed pack, thread stack, thread cache size. So these are other things that we can change to improve our server, but the main thing here is that we enabled this low query log. So the first screenshot is how everything was commented, and then the second screenshot is how we changed it. So we added this low query log, which enables this log query logging, and then we uncommented the log file location. We changed the long query time to 2, which means log queries lower than 2 seconds will be recorded there. Then log slow verbosity adds query plan info. Log query node using indexes detects unoptimized queries. And then log slow min examined row limit 100. It ignores very small scans. And this is a screenshot of the result we get. After enabling this low query log, I found this entry that shows a query performing of a full table scan. The query took about 0.004 seconds, which isn't long, but the log shows it examined 159 rows and created a temporary table, meaning the query isn't fully optimized. We can see that the explain output list is all and no possible case, indicating that no index was used. And then the full scan, yes, it confirms it scanned all rows in the table instead of using a targeted lookup. This information helped me identify where to add indexes or rewrite queries to improve efficiency. And even though this specific example is fast, in larger datasets, it can become a major performance bottleneck. And then we did performance analysis stop. This is just in the computer system. You just run the command top, and it shows the top systems in your computer that are occupying your CPU and your memory. So right now we see that MySQL is occupying 12.6% of our memory with MariaDB, and the rest are minimal compared to that. So in a larger data set, the CPU and the memory might be longer. So one thing that we might want to change in the future will be maybe expanding the CPU or expanding the memory, but as of right now, it is not necessary. And then different ways that we can improve the performance of our system. So the first way is by indexing. The first and most direct way to improve performance is through indexing. By analyzing query execution plans, we use explain, and we can identify where full table scans were occurring and create indexes on columns used in where clauses and joins, such as customer ID in orders and product ID in order items. Then we can do normalization. Although normalization ensures data integrity, in high-rate systems like an e-commerce, excessive joins can slow queries. So we could apply the normalization for frequently accessed data sets, for example, storing customer name and region directly in the orders table instead of joining customers. This would reduce the number of joins needed for analytical queries and speeds up threads, especially under heavy load. The next thing we could do is materialized views. To optimize repeated analytical queries, we could implement materialized views. For data like total orders per product and average review ratings, instead of recalculating these metrics each time, they could be pre-computed and refreshed periodically. This approach would drastically reduce computation time for dashboards or reporting queries. And then we could always add more nodes in the cluster. At the infrastructure level, adding more nodes to the Galera cluster distributes read and write operation across multiple servers. This could improve fault tolerance and scalability. Even if one node fails, the others remain synchronized. It would also balance their workload, preventing performance degradation under high concurrency. Let's see advanced ETL pipelines. So this is the code I use. So I'm gonna go pretty fast in this demonstration, but you can stop and look at it more in detail if you want. But overall, here I created the raw tables, which are like my staging tables, where the information was just loaded in bulk. Then we did the data loading into these raw tables, and then we cleaned these tables. So I cleaned all of them, but I want to show you specifically the where is it? I didn't with all of them, but here in orders we see that we cleaned the dates. So first in that raw table we cleaned it, and then we created a new clean table called order items, and then we inserted these clean and transform records into the actual table. And as I said, I've done this with all the tables, so they have all gone through this 3-staging process where just create the raw tables, all the data was inserted raw, then it was transformed for all the tables, and then it was implemented into the clean tables. And then here is a little demonstration on how we can see this in the Galera cluster. So here I executed that code that I was showing you before. MariaDB, source Milestone4, everything went okay, and here I did show tables, and we can see that we have raw categories and then the actual categories table. That was all the different tables, and then I did a select all from orders limit 10 just to show how the 10 orders that they're clean it works. And then we go to Galera B, we just go into AetherMart, show tables, we see that the tables are logged in there, and then select all from products, and we can see the products. It worked, they're clean, and our dataset is synchronized, and it's working. Let's see, now we're gonna move on to vectors. So first of all, I created a staging table for the products here, where I also put the description as text and embeddings as vector with 768 dimensions. And the second screenshot is what it is in the .env file, as well as the Google API key. And then this is the code that Professor Gamilian gave us. I just edited some minor things just so I could run it in my table. So the way I did this is I edited Gamilian's code, and then I downloaded the packs necessary to run this inside the EC2 instance, so I did not have to open the security group for everyone. That's a very high security risk that I did not want to go through that. So I just grabbed the code, I edited what it was necessary, and then I created a .py inside the EC2 instance, and I've run it through there. So this is the code. I'm going very fast again. If you want to stop this for a second to see what's in there, go ahead. This is just the code that Dr. Gamilian gave us with some minor changes. So it works for my tables. And then here's another video showing how this code is being executed in the EC2 instance and how it works. So I called it pembeddings.py, and here we see it working. It gave some expected errors, but then attempt 2 works. So it was just working as it should. I'm gonna speed this up a little bit, take some time, blah blah blah. Here it's working 4 out of 5. And then we have here 5 out of 5. And then it batch completed, and it still have 35 products still need processing. So I run this code over and over again until I did not see this message more. So then once that was completed, then I wanted to see that it worked. So we have 50 rows with a description and 50 rows with embeddings. Here's just another example of how it worked. And then I altered the table products, the original one, and I added the 2 columns needed for this, the description as text and the embeddings as not null. That's why we need to create these staging tables for this, because it had to be able to have nulls, but in this final table we cannot have nulls. So once we created that table, we updated this products table with the vectors and the description created in the staging table, and then we altered again the products table to add vector index that, and here it will be saved the distance as cosine. This is the code that Dr. Gamillion gave us. I just altered it so it works for tables once again, and here is just how the vectors work and how it runs the query, and it looks up for the most alike vector from a sentence given. In this case, it's a gadget for my kitchen. So this is just the code used, and then here is another video showing how it works. So first, this is the code inside my MariaDB, save the exit, and then we run Python 3. Python 3 lookup pi, that's just how I named it, and here it creates the similarity, the description, and we see that the product vary is the most similar one with a similarity of 0.5, and then we have option 2, 3, 4, and 5. And then we're gonna do the same thing but for review, so I'm gonna go a little bit faster through this. We'll create these staging tables. The code provided from Dr. Gamillion, but with some changes. It works now for the reviews. You can stop at any point to read if you want anything from here. Then here's a little screenshot of it working, creating the vectors, and then updating the databases until it was completed. We did this for 150 rows. And then we did the same, we altered the original table to add the embeddings, we updated the table, we did a little check to make sure that it was good, it was being updated correctly, and then we altered the reviews table again to add the index for the embeddings with the cosine as distance. And here we have again the code used for the search in the reviews. Here we changed the query. We put comments about durability and quality. So we're looking for the most similar review to that. So once again, this is the code. Stop if needed. And then here we have another video of how it works in Galera. Once again, this is the video inside Galera. Plug it up a little bit. It's the same code as shown before. And then here I just run it, Python 3 reviews lookup.py. And here we have the 5 most semantically similar reviews. It worked a little bit worse than before, but here we have the review ID, the number, the rating, and the text, and then the similarity for the 5 most semantic reviews. Then let's move on to refined AI data preparation. So for normalization, each product and review description was converted into a 768-dimensional vector using Google's text embedding 004 model. To ensure numerical stability and consistency, the vectors were normalized to range between -1 and 1, and normalization prevents any single feature from dominating a similarity calculation and improves the accuracy of cosine similarity and vector distance metrics using semantic search. Feature engineering. For this dataset, meaningful text fields were extracted and transformed into embeddings, product descriptions, and user review texts, which capture semantic meaning instead of just relying on literal word matches, like a normal SQL search, like select all when something very specific. Here is more vague and ambiguous, and you can just look up by semantic search, which is the ANN that we were talking about in class. These embeddings act as refined features, allowing AI models to understand contextual similarity between products and reviews. So for example, durable blender, it's kind of similar to sturdy mixer, but it's not the exact same. Then vector dimension. So in our case, each embedding consists of 768 numerical dimensions, representing unique semantic features in the text. This dimension size was chosen because it balanced semantic richness with computational efficiency, but maybe there's another dimension that works best for our case, and there are obviously other dimensions that work worse than our case. So now we're going to look at the advantages and disadvantages of higher dimensionality and lower dimensionality. So for high dimensionality, the advantages are that it has better semantic precision, it captured more weird relationship between words, improving similarity search accuracy, and the higher model expressiveness. It retains subtle meaning differences between similar reviews or product descriptions. And it reduced information loss. It's ideal for varied real-world language patterns in product and review text. But it also has some disadvantages, like increased storage and compute cost. Each vector requires more memory and CPU resources during distance calculations. So if we have a constrained CPU source, we might need to use less dimensions. Risk of sparsity. Some dimensions may carry minimal information, which can slow down query performance, and potential overfitting in smaller datasets. Models might capture noise rather than meaningful patterns. And then for lower dimensionality, like 128 or 256, some advantages are that it can be faster search performance, lower computational cost for vector distance or clustering operation, and smaller storage footprint, which is ideal for lightweight real-time systems. And the advantages of this lower dimensionality is that it reduces semantic accuracy, some contextual information may be lost, and it's a weaker generalization. The model might struggle to differentiate between subtle textual meanings. So for this project, AI was used, specifically ChatGPT. It was mainly used for troubleshooting and adapting the vector codes to my dataset and my case. It was heavily used for that and for understanding some concepts and how to implement this correctly and understanding what it does. From this I learned that AI can be very useful, but at the same time you need to give it a lot of context so it knows exactly what you want to do, because AI is not in your brain, so it doesn't know what you want to do unless you specifically express. But this might create a conflict if you are in a company working or you want something that's private. It might have some difficulty understanding what you're trying to do if you can't give all the information that it might need. So there's always that conflict when using AI. Thank you very much for listening. I hope you like my presentation, and I'll see you again for Milestone 5.